So, hello everyone, welcome to the class. Yeah, today I'll be continuing today's class as Gopi sir is bit busy. We will start with our class. Before starting the class, let me introduce myself, and meanwhile you can give your whether I'm audible or not. You can respond through the technical poll. I'm launching the technical poll, and people in the YouTube, you can as we are live now, you can give your responses in the chat. So if technically everything is fine, we can start. Meanwhile, let me introduce myself. My name is Alekia, and currently I'm working in JNV Hassan. Yeah, as you all know, I will be teaching chemistry, and I've graduated from National Institute of Technology, Rourkela. So yeah, meanwhile, you can give your responses. Fine. So as I can see, technically everything is fine from the Zoom side. We are good to start. Now from the YouTube people also, as technically everything is fine, we'll start the class. So today we are going to start the new chapter, that is chemical kinetics. So what you people know about this chemical kinetics, and let's start it with a kind of interaction one. What you know about this chapter chemical kinetics, you keep it in the chat box. We'll see how much you know and what are the things that we are going to learn. Let me see you what were your expectations from this chapter. So how you will be having, if we are talking about the electrochemistry, how you will be telling that we are going to learn something about the batteries and all those things. And if you are talking about the surface chemistry, we are going to talk about the how adsorption, how masks were prepared, charcoal masks or whatever masks that you are having, how these were prepared. So you will be having certain idea of all the chapters, right? And in the same way, why, when you're starting a new chapter, this first question comes into our mind. Why do we need to study this chapter? What were the applications based on this chapter? The first thing is it was there in your syllabus, so that's why I'm studying. It's not like that. It's not like that. So why do you need to study this chapter? And what are you going to learn from this chapter? You can put it in the chat. What are you expecting from this chapter? Fine. So let me just start by telling what this chapter gives you first. So let us just try to relate what is chemistry, and where this chapter lies in that part of chemistry. So whenever we are talking about chemistry, if I ask you to tell what is the first thing that comes to your mind when you're talking about chemistry, lot of people, I can assure that lot of people's your brain starts about the reactions, like the colors that they are showing, or the transformations from diamond coal to diamond and graphite, or rusting of iron, or any kind of water synthesis, Haber's process. So I can assume that what sort of things that were running in your mind when we talk about chemistry. Of course, it's all about exceptions. You will think, some of you might be thinking about chemistry is nothing but exceptions. So other than that, it is all about the reactions, right? Chemical reactions. And now when you talk about a particular chemical reaction, this all the reactions, how they were happening, you all know structurally how a reaction look like. You will be having a reactant, and then you will be having some kind of arrow, then you will be seeing a product. So this is how a chemical reaction was being represented, from your childhood, the way how you are seeing the chemical reaction. And when it comes to the chemical reaction and what were the things involved in it, there were three major things that you need to keep in mind when you're doing any chemical reaction. That is feasibility of a chemical reaction. So first thing is feasibility, whether the reaction is feasible or not. So feasibility is nothing but its synonym is possibility. So whether the reaction is possible or not, or the possibility. So which part of chemistry deals with it, whether the reaction is possible or not. Take 1 minute time and think about it. There are certain chapters, right? Physical chemistry chapters, organic chapters, inorganic chapters. Is there any such chapter which tells me whether a reaction is possible or not? Something related to enthalpy, entropy. Exactly. Like when you're talking about the thermodynamics, thermodynamics is a part of chemistry which deals with the possibility of a reaction. And you all know, if del G is less than zero, the reaction is spontaneous and feasible. If del G is greater than zero, the reaction is not spontaneous. So there is this part of chemistry called thermodynamics, which tells about the possibility or feasibility of a reaction. Now, the second part, like assume that, okay, fine, like whatever the whatever the reagents that I have took, A and B, for example, whatever the reactants that I took were having del G less than zero and the reaction is feasible, or the reaction is possible. Thermodynamically, it is stable. Now, what next? The second question that comes to our mind is how far this reaction is going to be happen. Like whether all my reactants are being converted into products, or only certain reactants are being converted into products, or is there any wastage happening? Like this extent of the chemical reaction part is will play a prominent role when you're dealing with any industrial processes. For example, like when you joined as a chemist, imagine yourself like a chemist joined in any laboratory, like after certain 5 to 6 years. So if you are joined as a renowned scientist, you will be getting this effort, or you will be getting this credit from your higher officials only when you stop wasting the reagents. So that is what the basic thing about the chemistry. So if you're taking reactants 100% and all the reactants were converting into products, that means basically I want to talk about the yield. If you are giving the yield as 100% yield along with the reagents that you're taking, if you are reducing the wastage of it, you will be getting rewarded, or you will be getting like appreciation from your higher authorities. So like if you are wasting a lot of things, that means if you are starting materials were not completely being utilized when you are converting a product, that means there is a lot of wastage. Next day I'm going to tell you, you will be out of that company. So your company will fire you, because companies or any industrial methods will basically work on this extent of reaction. Like they want all the profit with the less amount. That is how the industries work, right? So which part of the chapter, which part in the chemistry deals about this extent of reaction? Think about it, like which part of the chemistry deals with the extent of reactions? Huh. So tell me which part of the chemistry deals with the extent of reaction, whether like all the reagents were formed into products, or all the products were formed into reagents, or any equilibrium state. Yes, like I have used the word also. The part of chemistry that deals with the extent of reaction is chemical equilibrium. Like if it is dealing with the ions, you will call it as ionic equilibrium also. So in the equilibrium chapter, we have studied about whether all the reactants were converting or not, or is there any equilibrium position. If at all there is an equilibrium position, what is happening at the equilibrium position? So these were the things that we have studied. Now, like when it comes to the part, like as we have divided, first thing is also true. That means whatever the random reagents that I took, they were undergoing the feasibility, they were possible, they were thermodynamically stable, and the reaction is happening. Next question that came to our mind is like whether all the reagents were giving products or not. So the second one also, if I assume that all the reagents were converting into products, that means equilibrium part of the chemistry is also supporting. The extent of reaction is also known to you. The next question that comes to our mind is speed. Nowadays, like this is most important one. Like you want everything to be fast, right? You don't want to wait, and you don't want to spend much time on it. So that is why like this one shot videos or direct videos or these all things came up. So the same way, the speed of a reaction, whether it is fast or whether it is slow or it is moderate. So what is happening, like what is the rate of speed is nothing but rate. How it is changing at a particular time, or how it is changing in a particular interval of time. So that part deals with the chemical kinetics, which is nothing but our current chapter. So if you know about the chemical kinetics, you can able to tell what is a rate or what is the speed of a reaction. So when you are talking about a chemical reaction or random chemical reaction, how the feasibility extent plays a major role. The same way, the speed or the extent, the speed or the rate of a reaction will also play a major role. So to understand the speed or the rate of a reaction, we need to study the chemical kinetics chapter. So I hope the brief introduction about the chemical kinetics chapter was clear, and our major focus is only on this area, the speed of a reaction. So now we will go deep into the chemical kinetics. So as you can see, the name chemical kinetics, the name itself is a self-suggesting name. Chemical means what? Any chemical reactions that are happening, or any chemical processes that are happening. Any chemical process that are happening. And when it comes to the kinetics, the word kinetics is derived from the word kinetics is derived from kinesis, which meant movement. So like movement or speed or rate, all these three were synonyms. So how the chemical reaction speed is happening, or how the chemical reactions moment is happening, and at which rate they were happening. So all these things we will study in this chapter. So as you can see here, at what rate, at what velocity, like if you want to find out the velocity of a car, you will be doing, if what will do, you will calculate the speed of it and you will divide it with time, right? So the same way, when you are trying to calculate the rate of a reaction, you will be doing the same similar kind of expressions, like which I'll tell you in the next coming forward slides. Not just about the speed, also like how much, like as you can see here, like protein, like bread. So how it will happen? How it will happen? From how much time it will take? What is a like? This is a chemical reaction, for example. Like if you take spoiling of, like what is its rate of a reaction? So these were all the things that, so keeping all when you are treating any two reagents, as you can see here, reagent A and reagent B. So when they are coming close to each other, they were forming a product. At which rate, at which speed, what is the order of the reaction, what is the mechanism of a reaction, what is the rate of that particular reaction. So only this chapter, which is nothing but chemical kinetics. So these are the things that you will be learning in this chapter right from the beginning till the end. So we will start with the rate of a reaction, then we will see the factors affecting rate of a reaction. Please make this a note, because like in every class these things will not be taught. Then we'll study about the rate law, what is meant by a rate law, and what were its relations. And so, yeah, majorly what I meant when we are talking about the factors affecting is like how a temperature factor will affect and how a concentration factor will affect. So when I'm talking about the temperature one, we will also talk about Arrhenius equation. I'm just giving you a roadmap of this whole chapter. Our Arrhenius equation will be occurring, and in the concentration, this is very like interesting one, where you will be seeing first order equation, second order equation, zero order equation, third order equation. So you will be studying in detail about all these rate of reactions and their half-lives, their different set of formulas. So these all things will be coming under chapter rate of reaction. Next is like molecularity. In like after rate law, it is molecularity, and finally we will end up with the mechanism of a particular chemical reaction. So these were the major topics that involves in this chapter. Let us first start with the rate of a reaction, as that is our first chapter. So in first topic. So in today's class, we'll try to complete the rate of reaction. And in the upcoming classes, we will be studying about the factors affecting rate law, molecularity, and mechanism. So without any waste of time, let's start with the rate of a reaction. So as I have told you, like when I showed you a car, I have talked about the rate, like rate in terms of speed, right? So what is meant by speed? What is meant by speed? How do you calculate the speed of a particular car? How do we calculate the speed of a particular car? So the same car has come here again. So how do you calculate is change in its position by change in time. That is how you calculate the speed, right? And similarly, you can calculate for a reaction. So change in the position as it is not moving, what we'll do is it is changing in terms of concentration. It is not changing in terms of distance. When you talk about car, I'm just trying to depict both the things. That means I'm trying to relate both the things. How you will calculate speed is exactly same as how you will calculate rate. For the calculation of speed, you will see the change in position, that means change in terms of distance by change in time. And when you talk about the reaction, it is nothing but change in concentration with respect to time. So it's as simple as that. When someone is asking you, tell me a rate of a reaction or speed of a reaction, just calculate what was the difference in the concentration and with respect to time, how much it has changed, whether it is diluted or whether it is concentrated and in which particular time, then you will be getting the rate of a reaction. So when it comes to the units, as you can simple see it, like there is no rocket science involved in it. As you can see on the screen, concentration, how you will write it, like concentration by time, how you will write it in terms of units, mole per liter. Concentration is mole per liter, and time is second. You can also write it as mole liter inverse second inverse. So this, if you are talking about any solutions, solutions may change will happen in terms of concentration. If you're taking in terms of gases or in terms of any partial pressures, if not in terms of concentration, if you are taking in terms of partial pressure, the unit will be, if you're taking in terms of pressure, the standard unit is atm by time is second, so it will be atm second inverse. So these were the units that we generally use. Like if you're talking about the concentration, it will be mole liter inverse second inverse. And if you're talking about the partial pressure, it will be atmosphere second inverse. So just I'll take a pause here, and like if you have any questions related to anything that we have learned till now, what is meant by, like why are we studying a chemical kinetics chapter, what is meant by chemical kinetics, what is meant by a rate of a reaction, how do we calculate the rate of a reaction, and what is the unit of the rate of a reaction in terms of concentration as well as in terms of pressure. Till all these things, if you have any doubt, let me take a pause here and take your questions. So it's time for your questions. You can put your questions in the chat box. If you have any queries or if you have any questions, you can put it in the chat box. So I'll wait here for 10 seconds to take your questions. Please type your questions. If you don't have any questions, that would be great. If you keep yes or you or clear in the chat box, it will help us to, like start fast. So take this 10 seconds time and put it your doubts. If you don't have any doubts, put yes or no in the chat box. We'll move ahead. Fine. So as I get like few of you responded that it was clear, And as none of you gave any questions, it meant that it was clear. So let us move ahead. And let us see what is like, what are we going to see the, just a second. Okay, just a second. There is some issue. Like, let me sort it out. So yeah, due to some internet issues, so my screen got stopped again. Give me a minute. I'll just fix it and come back. So yeah, sorry for the inconvenience, and I'm launching the poll again for the technical one. So just just tell me whether you can, or you can put it in the chat only directly. You can put it in the chat whether my screen is clearly visible or not. So check it, fine. So as the screen is clearly visible and my voice is also clearly audible, let's just continue from where we have left. So we have seen this, nothing but the speed is nothing but the rate, like how the change in concentration will happen, how the concentration change will happen. Now let us try to understand this rate of reaction a bit more clear. So is like the question that comes to our mind is like, can I calculate this rate of reaction For all sort of reactions, can I calculate this rate of reaction by using this change in concentration by change in time formula? For all the reactions, no. First, like to understand what is meant by all the reactions. What were the possible reactions that we had? So we'll just try to see what were the types of reactions, and then we will segregate for what type of reactions we can calculate the rate of reaction, and for what type of reactions we will not be calculating the rate of reaction, and what were the reasons for it. So as you all know, there were the three basic types of reactions, which are fast reactions, moderate reactions, and slow reactions. So when it comes to the fast reactions, any reaction, if that is happening like very quick, very fast, so you will call them as fast reactions, which will be taking only fraction of seconds time. That means if the reaction is getting completed within 10 seconds or within 5 seconds or with less than a minute. For example, if I take a glass of water and if I add a blue color ink or black color ink to that glass of water, will it take years of time to show the color in the glass of water? No, right? Like within that fraction of seconds, you will be seeing the color of that particular reaction, like color of that ink in the glass. So that is very fast kind of reactions. And when it comes to a moderate reaction, like when you are preparing milk from curd, will it take years of time to have to give us curd from milk? No, right? Or will it happen within just 10 to 15 seconds? Like as soon as I bought milk and if I add a curd, will it be happening within just 30 seconds? No. So it is a kind of moderate reaction, not too slow, not too fast. And when it comes to the slow reaction, the best example for the slow reaction is rusting of iron. It will take years of time. Like if you take any iron, if it is getting exposed to the air, like which is containing moisture again, if it is getting exposed to that like that atmosphere for continuously 3 to 4 days, or for continuously 1 day or 2 day, you'll not be seeing that much of rust on it. But if it is left or kept in that way for the continuous years, for example, for 1 year or for 2 year, you will be seeing the reaction happening very slowly. So these are the three examples of fast reaction, moderate reaction, and slow reaction. As we had a clear idea of what is meant by a fast, moderate, and slow reaction, we'll try to understand in detail how the rate of reaction will be changing in the fast reactions, how it will be varying in moderate reactions, and how it will be varying in the slow reaction. Now, if I take a fast reaction, here HCl and an indicator. You can ask me, ma'am, HCl, so it will not be in a orange color, but you are representing with an orange color. See, here I have added HCl along with that some methyl indicator, which is like in an orange color or as an indicator. So after that, I'll be getting a neutralized reaction. You all know that is the reason for it is formation of NaCl and water. Yeah. So formation of NaCl along with H2O. You will be getting a neutralized solution. So, and if you take this reaction, which is exactly same as adding ink to the glass of water, like fast, very fast, you will be seeing very fast color, or you'll be seeing very fast reaction. Del T, that is change in time, is very small. R is that reaction time is very, or is the extent of reaction is very high. So in these cases, you cannot calculate the rate of a reaction. Example are all the acid-base reactions or all the ionic reactions precisely were the fast reactions. Adding salt in a water, ionic reaction again, NaCl into H2O. It will not take years to dissolve that salt in a water. As soon as you add it, it will be getting dissolved in the water. That is very quick. So for such kind of reactions, you need to, you will not be getting a variation in the time. You will not be seeing they're very quick. Within fraction of seconds, the reaction will happen. So you will not find out exactly or clearly or particularly the rate of a reaction. So in the fast reactions, you will not be calculating a rate of reaction. But when you come to the moderate reaction, where here I have taken the example of hydrogen peroxide, 2H2O2, and if it is like forming into water and oxygen, it will not take too much of time, like too large time, or it will not take too small time. So here my delta T is moderate, like how we have seen an example of milk turning into curd. Milk turning into curd, it will not take years of time to turn into curd, and it will not be happening within, like, 30 seconds also. It will be taking certain period of time which is moderate. So in the same way, for a chemical reaction like hydrogen peroxide giving water and oxygen, it will also happen in a moderate period of time. The delta T, or the change happening for the reaction in a particular time, will not be too high or will not be too slow. So in this case, at certain particular of time, we can calculate like what is the rate, exactly what we are doing when we are trying to find out the rate of a reaction. We are doing change in concentration by change in time. So here, if my delta T is not zero or not infinity, I will be finding a rate of reaction, right? So that is what all about the moderate reaction. So for the moderate reactions, we can find a rate of reaction. We cannot find for the fast reactions as delta T is very high. Now, when it comes to the examples, like other examples other than hydrogen peroxide, inversion of cane sugar and the hydrolysis of starch, these will also come under moderate reactions. Now we'll move ahead and we will see about the slow reactions. So what is meant by slow reaction, which will happen for the best one, which will happen for the longer time, as it is half revealed, and I have told the same example also when I'm talking about the slow reactions. That is rusting of iron. Rusting of iron will take years of time. It will not be like the salt dissolving in water like fast, that much fast. It will not be like milk turning into curd like within 1 day or 2 day. It will be like years of time, like for the iron to get rusted. If you keep it, iron metal, if you keep it aside for the 2 to 3 years, then only it will start showing rusting. So that is one of the slow reaction where delta T is completely infinite. Delta T is infinite. So in that case also, you cannot find a rate of reaction. So the major point of in this fast reaction, moderate reaction and slow reaction is we can only find the rate of a reaction when we are having a moderate reaction, where delta T can be calculated. So other than this rusting of iron, like some of you were asking, like few more examples of this rusting of iron were when we are talking about the diamond, like graphite converting into diamond. So that is the reason why diamond is costly. Like if you take a graphite, even the generations pass on, you will not be seeing diamond because it will take very lot of time. So that is one of the thing, conversion of graphite to diamond, and as you can see the example rusting of iron. These are some of the reactions. So our major point is moderate reaction. So for example, now as we are good to start with all the basic things. For example, let us take a reaction something like this: reagent giving some arrow, which we were seeing right from our childhood, like how exactly a typical chemical reaction looks like. Reagent, arrow, and the product. So this is let us take a chemical reaction. So now what will happen when we are dealing with a chemical reaction? Reagents, what will happen, and products, what will happen? Reagents will be consumed, they will be reducing, and product will be forming. Initially reagents will only be there, and finally product will only be there. For example, take this reaction like forming or preparing a tea kind of reaction. So initially, what were your reagents to prepare a tea? You need tea leaves, you need sugar, you need milk. Okay, fine. Like these were the basic things, right? So if you take these as a reagents, and if you take product as your cup of tea, initially you will be seeing tea leaves separately, sugar separately, and milk separately. But in the process of making this reagents, or in the process of making this tea into a product, there is certain point where you will not be seeing tea, sugar, milk separately. And there is certain point where this all the ingredients were converting into tea. So initially you will be having only the reagents, that is only the ingredients. And finally, when you have a cup of tea in your hands, you cannot bring back the tea separately, sugar separately, and milk separately, right? So at the end, you will be having a product where the reagents during the product time will be zero. So such kind of reaction I have taken here. That means only a forward reaction. So reagents will be decreasing, product formation will be increasing. So now, like, keep these two things in the mind. We will find the rate of a reaction separately, like how the reagent is happening and how for the product is happening. So as you can see here, rate of disappearance of R, I hope as it is being consumed, as it is getting being used, or as it is getting disappeared, we will call it as rate of disappearance. And as it is a reagent R, we are using R. So how do you find out the rate of disappearance of R? Like rate of reaction only. How did we find out the rate of reaction? Change in the reaction by change in time. So here change in the reaction is nothing but change in that reactant size, that is change in the concentration of R by time taken. So whenever I'm telling change in concentration, the change is happening how it is decreasing, right? It is not increasing. So that's why instead of writing change in concentration of reactant, we have mentioned it as decrease in concentration of reactant by time taken. And when it is decreasing, we will be using minus sign. So the signs were very, 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 very important. When we are talking about the disappearance of reactant, the reactant is getting decreased. That means it is going into the negative one. So you have to represent it with the minus. So always, always, and always, rate of disappearance of the reactants will be represented with the negative sign as the reactants were getting decreased. Now let us come to the appearance of the P. That means appearance of T. So what is happening? Change in concentration of P by time taken, like exactly how we have seen in the previous one. Change in concentration of P means how it is happening to the concentration of P. It is increasing or decreasing? It is increasing, right? So increase in the concentration of P by time taken. So if it is increasing, we will represent it with plus. So sign matters a lot. If it is appearing, it will be a plus sign. So these are the basic formulas about the rate of disappearance of R and rate of appearance of P. So I hope you understand why we are using disappearance term for reactants and appearance term for products. Now let us come to the interesting part of this chemical reaction, that is graphs, like exactly how the exact reaction you will get to know the speed or any concept when you understand the graph nicely. So here we are actually going deep into the topic. Now if you take a graph between the concentration and time, between the concentration and time. So to make you understand clear, reactants graph, as I have represented reactant with green circle. So wherever you are seeing the plot of green is all because of the reactant one. And whenever you are saying a plot between blue, that is related to the product one. Now, as you can see, what is the concentration of the reactant at initial time? Initial time, it is 0. As you can see the plot here, initially you will be having at time 0, all the reactants will be there and products will be 0. Now, when you go on increasing the time, the reactants concentration will be decreasing because the individual form of seeing them separately will be decreasing, and at certain time the concentration will be completely decreased or it will be completely becoming 0. So this is what all about the reactants one. And at a particular time t1, whatever the concentration, you will be representing with R1. So this is at particular T1, the concentration is R1. At particular T2, the concentration is R2. Now, what I want you to understand is T1 is the initial time where the concentration is high, R1 is higher, And if you talk about the T2, delta T2, delta T, like after certain T, the concentration is decreasing. The concentration is decreasing. That is the reason why we are representing with the minus sign. How exactly the scale will look? How exactly the scale will look like from 0, 1, 2, 3, 4. So when you're talking about the change, that means uh, R2 minus R1 divided by T2 minus T1. So for example, if you are doing this like rate of reaction, R2 will be what? 1. R1 will be what? 2. 1 minus 2 by, for example, it is of 1 second and 3 seconds. So 3 minus 1. So you will be having minus 1 by 2. So this minus sign is because of this reason, where the concentration is decreasing. R2 will be lower than the R1. So I hope you understood with this example like 1, 2 and all. So this is what about the reagents one. Just put it S or clear in the chat box if this concept is clear, because more and more if we go, if you don't understand this one, there is no point in going forward. So this is very simple one. Just keep a message if you are clear about this one. And if you want me to explain any of thing again, I am here, like I'll be explaining it to you. So just confirm me whether it is clear or not through your chat, so that I'll get to know whether you people understood, or do you want me to repeat it or anything we had. We will sort it out. Fine. So we will talk about the blue line. That is nothing but the product one. So as expected, product initially at time 0. At time 0, you will not be seeing any product. Like if I keep the tea leaves, sugar and water, and if I sit like that, will I be getting any tea in the initial stage? No, I'll not be getting any tea. So here the ingredients will be in, here the products will be in 0 state. But as you keep on increasing the reaction process to happen, at certain like at particular time, the entire reagents will be completely converting into products. So this is how the product concentration will increase. Now we'll see the same thing at particular time T1, P1 will be there, and at particular time T2, P2 will be there. As you can see here, it is exactly reverse now. So if you want to find out the rate of appearance of P, it will be the same thing, P2 minus P1 by T2 minus T1. So if you order 1, 2, 3, 4, so it will be 4 minus 3 by 0, 1, 2, 3. 3 minus 1. So it will be a positive value, 1 by 2. So it will be a positive sign. So that is how exactly why you are seeing negative sign and positive sign, because of their plots. So I hope this rate of appearance, rate of disappearance of a reaction was clear. The formulas were clear. As concentration of reactant is decreasing, so we are using by -1 to make the rate of a reaction whole positive quantity. To maintain the reaction whole positive quantity, we are multiplying with the -1. So that is nothing but what I have explained you till now. Why we are using minus sign and why we are using plus sign. So here are the few examples. Let me solve for you for the first one. The next one you can take it as a homework. How do you write? Take this as a homework. Now let me solve you for the first one. How do you write the rate of a reaction for this one? So whenever you are having a, till now we have seen only the simple form, right? Reactant and product. Now we are having the reactants with the stoichiometric coefficient. How will we do is 1 by 2 stoichiometric coefficient into change in concentration of A by change in concentration of time T plus 1 by 3 change in concentration of B by change in concentration of time T equal to, I mean, like this is not plus, this is equal to, just let me erase this one, equal to 1 by 4 delta C by delta T. If you can see, I didn't represent the signs. I have left it like whether you will identify it or not. As you can see, the reagents A and B will be represented with minus sign as they are getting reduced, and the product product which is C should be represented with positive sign as it is appearing. So here it will be minus 1 by 2, minus 1 by 3, and this will be plus 1 by 4. So try to write down the same kind of rate of reaction for this one. But for this one, along with the rate of reaction, try to write down rate of appearance as well as rate of disappearance formulas. Let us see how you will write it. So no issues, like in the next class, first we will discuss about this question only, and we will write together like rate of reaction as well as rate of appearance one and rate of disappearance one. So as this thing was clear, let us move ahead and let us talk about the average and instantaneous rate of a reaction. So how this rate of reaction was separated, like what were the types of rates of reaction that we can see? Average and instantaneous reactions. So as you can see here on the screen, okay, fine, I couldn't able to play this. So yeah, so as you can see on the screen, who is he? I think most of you know it. Not most of you, everybody will be knowing it. So as this fever of cricket is going on, like, yeah, this is our very own Virat Kohli. For example, why suddenly I have brought him into the chemical kinetics chapter is to make you understand the difference between the average rate of a reaction and instantaneous rate of a reaction. For example, a person like a cricketer only, I'll try to explain. A bowler has like, how many overs will be there in a over? 6. So a person bowled over first ball, second ball, third ball, fourth, fifth, and sixth. So for example, if he has bowled 6 overs and 1 over with the 6 balls, and this was the balls and this was the score. So in the first ball, Kohli scored 0 runs. In the second ball, Kohli scored 1 run. Next here, like, we'll make him only the on strike. So he has scored 2 runs. Then next he has scored 0 runs. Next he has scored 4 runs. Next he has scored 4 again, and then 0. So if I ask you to tell the what is the average score that a Kohli scored, how you will do when you are calculating the average score? You will be calculating the scores of all the balls, that is nothing but 4 plus 4, 8. 8 plus 2, 10. 10 by overall balls that he has delivered. So that is how you will be calculating, right? If I ask you to tell about the average runs that Virat Kohli scored in a particular over. So 10 divided by 6 will be something around 1.66, right? But in the same way, if I ask you what was the run scored by Virat Kohli in the third ball, it is 0. It is 0. So at a particular instant of the ball, you are getting one answer. That means you are getting one value. And when you are talking about the average, you are getting another value. So this average and instant were completely two different things. Whenever you are taking any rate of a reaction, for example, this is the same table how our scores table look like. So this is the reaction table and this is a time one. So the product formed is 1 at 1 minute time. Later it was 0. Sorry, product formed is 0 at 1 minute time. Later it was 2 for next 5 minutes of time. Later it was a 4 for next 10 minutes of time. So like if you are having this kind of data, if I ask you what was the reaction change happened in that particular what was the rate of a reaction that change happened in the concentration of the reactant over time. So how you will do average ke liye, you will calculate average by considering from first to 10 minutes of time. So if this delta in terms of minutes. But if I ask you about the what is exactly happening at second minute time, how much amount of product is forming at second minute time. or how much amount of product is forming at 5th minute time. So you can clearly see from this table at 5th minute of time, I am getting only 2% of the product. So if it is exactly confined that particular time, you will call that as instantaneous rate of reaction. If it is confined to an average one, like if it is confined to a range of delta t, that is from 1 minute to 10 minute or 10 to 20 minute, you will calculate it as an average rate of a reaction. If someone asks you what is happening at the 3rd minute of a reaction, what is happening at the 4th minute of a reaction, you have to calculate the instantaneous rate of a reaction. If someone asked you how the change in a reaction is happening for the first 10 minutes, you have to calculate the average rate of a reaction. I hope these two things difference was clear. How a average rate of a reaction looks like and how a instantaneous rate of a reaction looks like. So more in detail about this average and instantaneous rate of a reaction, we will see in the next class. Like as you can see here, average rate of a reaction is nothing but the same delta change in concentration by change in time. Okay, let's complete this average and instantaneous, and then we will wind up today's class. So when we are talking about the average rate of a reaction, how you will do is like exactly same as how we have understood the rate of a reaction. If you are talking about the rate of appearance, rate of disappearance of R, we will be using this formula minus del R by del T, that is nothing but R2 minus R1 by T2 minus T1, how I explained you. Only now concentrate on the blue line. Reactant to product. So at particular time T1, what is the value of R1? What is the value of R2? So it is negative sign, and appearance of product P, del P by del T. So P2 minus P1 by T2 minus T1. So this is a story about like the same one as the rate of a reaction, how we studied. And when it comes to the instantaneous rate of a reaction, as I said, the rate at particular moment of time. And how you will do it, like instead of using del, which is a change in time, you will be using a limit where del T is tending to 0, or you can use it as small d, where that is meant by small change in a reaction. Small change in a reaction at that particular small change in time. So practically, how do you with the graph, how you will find it is taking the same blue graph, how the reaction will happen. But this time we are not taking two time frames like this dotted lines, and we are not doing the del D, del T, P by del T. We are just taking one particular point in the curve and we are drawing a tangent to it. We are drawing a tangent to it, and from that tangent, we can find the slope m, and we can do the calculation of the instantaneous rate of a reaction. So this is just a brief idea about the instantaneous rate of a reaction and the average rate of a reaction. So with that, take this question as a homework question. And yeah, that's it for today's class. If you have any doubts, you can put your doubts in the chat box. If not, I am launching the teacher NPS. Okay, fine. The NPS was like I couldn't able to launch the poll. It's okay. You can give your feedback in the chat, how you felt about the class. You can give your feedback through the chat. People in the YouTube also, you can give your feedback through the chat. And yeah. Thank you, Sushri. So tomorrow we'll see, like if possible, we'll be continue, like whoever it is, like we'll be continuing from this part only. Yeah. So as I can see no questions in the chat box, I'm ending the class I'm ending today's class here, and thank you everyone for the response and participation. And yeah, welcome. You can leave the class if you don't have any doubts, and the people in the YouTube also, you can leave the class if you don't have any class. If you have any doubts, you can put it in the chat. So I'll be waiting for you for the next 30 seconds. Later, I'll be ending. Welcome, Sanya. Welcome, Sushri. Okay, like some of you are asking which college I am from. Yeah, right now I'm working in JNV Hassan as a chemistry teacher. and I have graduated from National Institute of Technology, Rourkela. I took both my bachelor's and master's from the same college. Like, fine. Yeah, welcome, Zain VD. Fine. So I'm ending the class now. As I could see no doubts from you people. Thank you, everyone.